synchronous demodulation in DSBSC. Synchronous demodulation in DSBSC. Okay. Now we will take a multiplier followed by low pass filter, followed by low pass filter. Here we will supply asynchronous means same carrier as that of transmitter, same carrier. Okay, synchronous means same carrier at transmitter comma receiver. That is called synchronous demodulation. Synchronous demodulation means same carrier at transmitter and receiver. Okay, and we will multiply, apply to low pass filter, so we will get the output. Output is a replica of same input. Okay, replica of input. Demodulated output. This is called demodulated output. Okay, so already we know S of t means M of t into C of t. M of t into C of t. Okay, again the output here, if I take this output as V1 after the product modulator, after the product, okay, after the product multiplier, V1 is nothing but S of t into C of t. S of t into C of t. So if you see here, this is nothing but AM cos 2 pi FMT and AC cos 2 pi FCT. And now again we are multiplying this with another carrier. This complete is S of t. Okay, so I will just write AM cos 2 pi FMT into AC cos 2 pi FCT. This is our S of t, into we are multiplying the C of t, AC cos 2 pi FCT. So we have 2 times cos 2 pi FCT. Okay, so what we will have, AC square cos 2 pi FMT into cos square 2 pi FCT. So this cos square can be written as 1 plus cos 2 theta, 1 plus cos 2, okay, 1 plus cos 4 pi FCT divided by 2. Okay, so when we apply this to low pass filter, higher frequency components are neglected. Higher frequency components are neglected. Okay, so at low pass filter, all the higher frequency, 4 pi FC is higher frequency. FM is low frequency. We know message is low frequency. Okay, M of t is low frequency signal, which is FM. And C of t is high frequency signal, which is FC. So FC will be cut off at the low pass filter. So final output, what we are going to get, is nothing but, okay, half AM AC square. Okay, this is low frequency. So cos theta, when theta is very small, you can see sin theta equal to theta when theta is very small. Okay, very small. And similarly, cos theta equal to 1 when theta is very small. Very small means close to 0, cos 0 equal to 1. Okay, cos 0 equal to 1. That's what I am trying to tell you here. And here theta means this 2 pi FM. This 2 pi FMT is nothing but theta. Okay, when theta is very small, the value becomes 1. Theta is very small, value becomes 1. Okay. Otherwise, what we can do, another way what we can do, I will write this as AC square. Remaining thing I will write as M of t. Okay. So M of t is nothing but this AC cos 2 pi FMT. I am writing it as M of t. Okay, like that also we can take the final output equation. So in that case, this theta very small, we are not using. So just I will erase not to confuse you with too many things in the same slide. Okay. So I'm not taking that option. So I am replacing this with M of t. Okay. And here, if the and receiver are using same carrier, transmitter and receiver are using same carrier, okay, then output is half AC square M of t. If they are not same carrier, output is half AC cap, because height is different at the transmit receiver. Carrier signal height is different. So AC cap I am writing M of t. Okay, this will be the output. If there is a phase shift between the carriers in transmitter and receiver side, used carriers, if there is a phase shift, output is half AC square M of t cos pi. This is the phase shift. Cos pi, this is the phase shift. If this pi equal to 0, output becomes 0. That is called quadrature null effect. Okay, this quadrature null effect will occur both in AM as well as DSBSC when the carrier is having a phase shift. Carrier at transmitter and carrier at receiver, they are having a phase shift. Okay, so output is 0 when pi equal to, okay, 90 degrees. Cos 90 is 0, no? Cos 90 is 0. So when pi equal to 90 degrees, then output is 0 when carrier at transmitter and receiver are having a phase shift of pi equal to 90 degrees. Okay, this is called quadrature null effect. Okay, this phenomena is very important. Output 0, this is called quadrature null effect. So what we are discussing in this entire slide, I will tell you the story what we have discussed. The diagram represents demodulation at receiver. Okay, how we are trying to get back the original signal. And this is the process. We are applying S of t and then multiplying C of t. Whether the C of t is same carrier as that of transmitter, because we are presently at receiver side. Demodulation means at the receiver side. Okay, demodulation means at the receiver side in DSBSC. Whether the carrier C of t here is same as that of transmitter, or they are different or having phase shift. These are the three different cases. Okay, and I have written some equations. You need not worry about the equations. Don't remember any of these equations, no problem. But the final output, it is very, very important. Okay, final output, it is very, very important. Half AC square M of t. Half AC square M of t. This final equation is very, very important for synchronous demodulation. Synchronous demodulation output. Okay, synchronous demod. In this entire slide, you remember only what I have kept in box. One box is M of t. Second, the circle. In white color, I have made a circle, no? When the carrier is different with a phase shift of 90 degrees between the transmitter and receiver, output becomes 0 because cos pi equal to 90 degrees, output becomes 0. This phenomena is called quadrature null effect. This phenomena is called quadrature null effect. In this entire discussion, you remember only these two things. Okay. So when pi equal to 0, there is 90 degree phase shift between carriers at the transmitter and receiver. Then output is 0. That is called quadrature null effect.